Today's topic is homogeneous linear equations with constant coefficients. This is going to lay down the framework for the rest of the unit because it's all going to be based on how we treat this. Before we get going, we're going to kind of just review a little bit of background that you kind of need to know in order to actually follow where the solutions are coming from and what's going on. Okay, so let's start with that. Complex numbers. Never thought you'd see those again, right? Look like what? Okay, good. A plus bi. We can graph these in a complex plane where the x-axis really is going to denote the real part of the number, and the y-axis would be the imaginary part. So in this case, from the origin to here would be what length? A. And then from the origin up to here would be what length? What's the coefficient of the imaginary component? B. So that's just B. If we think kind of like we did in polar, draw a little angle here, theta, with respect to positive x-axis. Call this distance from origin to our complex point r. Then we get a few relationships that we're going to make use of. Obviously, we know that r squared is going to be a squared plus b squared. A would be what? R cosine theta. So then B would be R sine theta, just using your SOHCAHTOA relationships. Okay, so then from here, any complex number, let's call it z, equal to a plus bi, can also be written just plugging in a and b into the equation as r times cosine theta plus r sine theta times I. And if you've done math team, you've probably become accustomed to this. Factor out an r, you get r times cosine theta plus I sine theta. Sometimes abbreviated as r cis theta. Okay, so that's where that comes from. So any complex number, and for that matter, even if it doesn't have the imaginary part, we could also write it in this manner. We just don't have the I sine theta portion. Okay, so we need to know a little bit about that. What else? A little bit of series. So again, this is stuff, maybe you've overlooked this, but hopefully this isn't too odd. If you've done math team, it should be pretty familiar. If you did a good job in pre-calc, you may or may not have done this. Okay? You did this in calc last year. Anybody remember what this series converges to? It's the sum of what? Say that louder, sorry.
It's the sum of all basic power, integral power of x squared plus 1
Which, yes. So take that and then Junwan, what is it equal to? E to the x. So if you write this out, okay, if you actually go term by term, you get 1 plus x to the first over 1 factorial plus x squared over 2 factorial and so on, right? And this does converge to e to the x. Let's do a couple more. Only the ones that we need. This is cosine. Okay, so if you don't remember that this formula is equal to cosine, you might have remembered it more in its expanded form. If you actually write it out, it's basically this this sequence, but what? Only the even ones and signs alternate, right? So it's 1 minus x squared over 2 factorial plus x to the 4 over 4 factorial minus and so on. Okay? Which other one do you think we're going to need? Sine. And that is the sum from n equals n to 0, n equals 0 to infinity, sorry. Yeah, 2n minus 1. I'll do it as 2n plus 1 in the denominator. Negative 1 to the n, and then x to the 2n plus 1. You could do 2n plus 1, 2n. It doesn't really matter as long as you get odd, right? And you can start it wherever you want. This is sine x. And then this is going to be the odd terms. So x to the first over 1 factorial minus x cubed over 3 factorial plus x to the fifth over 5 factorial minus all the other stuff. Okay? So, complex numbers, Taylor series. Okay? Let's put them together. If we let x equal I times theta in e to the x, then we have e to the I times theta. And now I'm just going to plug in using the Taylor formula. Okay? 1 plus x over 1 factorial plus x squared over 2 factorial, except I'm going to have i's and thetas, right? So we're going to have 1 plus I times theta plus, what's the next term? Using this guy right here. N equals 2 gives us I squared theta squared over 2 factorial. Does that make sense? Plus, what would the next one be? There we go. I cubed theta cubed over 3 factorial. We'll do one more just for good measure. I to the 4 theta to the 4 over 4 factorial. Okay. We good with where this is coming from? Just plugging it into the Taylor series, right? Now, let's group things. Like, for example, we're going to have a whole bunch of real stuff in this expansion, right? This is just real. This third term is just real, right? Because I squared is what? Negative 1. This fifth term is just real because I to the 4 is 1. So basically we have positive, negative, positive. You guys see what's happening here? So I'm going to put those together. 1 minus theta squared over 2 factorial. And then my next term was this guy over here, right? I to the 4. So that's plus just 1 times theta to the 4 over 4 factorial. And we didn't write it down, but what would the next term be? Minus theta to the 6th over 6 factorial, and so on. Okay, so all I'm doing is taking the Taylor expansion of e to the x, plugging in I theta, grouping all my real stuff first, and now what I'll do is factor out an I from all the imaginary terms. Yes?
Is that proof that says that usually I equals
Oh, well, you ruined the surprise. Yes. You know where this is headed. Okay? And we really need that for the rest of the section. So, if you factor out an I, you get theta. Here, if you factor out an I, you get I squared, which becomes a negative 1, theta cubed over 3 factorial. Factoring out an I from the I to the 5th term gives you I to the 4, which is positive, so theta to the 5th over 5 factorial minus, and you get the idea. Okay? So hopefully with the background, you don't have too hard of a time seeing what these guys equal. In the red is the expansion for what function? Cosine. So that's cosine of theta plus I. This is sine theta. So we get that e to the I times theta is equal to cis theta, or cosine plus I sine theta. And this is known as Euler's formula. And yes, this is where the prettiest equation in mathematics comes from, right? You guys have seen those everywhere if you're on math team, on those cheesy math team shirts and things like that, right? What am I talking about? E to the pi I plus 1 equals 0. You can just plug in pi into theta and you get exactly negative 1. Okay? So pretty because we have transcendental numbers, imaginary, real, and somehow they combine to equal 0, which is pretty awesome. Okay, so this one we don't really care too much about. This one we'll make a lot of use of. Okay? Any questions so far? All right, now we'll get into the diff EQ part. Okay, so as far as some of the stuff we've been doing, we know that for dy dx plus ay equal to the 0, it has a solution y equals c1 e to the minus ax. From experience, or if you actually want to go through and do it in your notes later, you can separate and do all that fun stuff. You're going to get this solution. Okay, so we know this. What we're interested in today is higher order stuff. So what about higher order equations? So for instance, wow, that had some distance. For instance, ay double prime plus by prime plus cy equal to 0. So particularly the ones that have constant coefficients. Here we have a second order equation. Educated guess is that, for this first order we had an exponential function, e to the something x, right? We're going to assume that maybe y equals e to the mx is a solution. Okay, so from experience, we had constant coefficients here. We had an exponential as our answer. Maybe when we do higher order, we're going to have that involved somehow. Okay, and if that's the case, we're going to go through and see if that's true and how that works out. Okay, so if this is a solution, then we should be able to take its derivative, plug it in, right, and see that it makes sense. What's y prime going to be? Me to the mx. Y double prime? So, now when I plug this in, we're going to take a y double prime, which is now m squared e to the mx, plus b, plug in y prime, that's me to the mx, plus c times y, which we're going with e to the mx, equal to 0. And now if this is a solution, I can factor out e to the mx. What's left? Quadratic in m, am squared plus bm plus c equal to 0. Obviously, this guy is never going to equal 0, right? So that means that if y equals e to the mx is a solution, then m, this m up here, which is also in this quadratic, right? Did I just write them? Sorry, my brain was a half step ahead of me. Then m must be a root of am squared plus bm plus c equal to 0. This is called the auxiliary equation or characteristic equation. Okay, any questions so far? Should all make sense. All right, so now, if m is a root of this quadratic equation, there are 3 different kinds of m's that we could have, right? First case, the auxiliary equation has 2 real roots. Let's call them m1 and m2. So that's the usual quadratic. You run the quadratic formula or factor, you get 2 real answers. We're calling them m1 and m2. Okay? So then, that's going to imply that one of my answers is e to the m1x. And what's the other one? E to the m2x. Good. And now if we put everything together that we've been talking about in the previous sections, we want to find the general solution, right? General solutions come from a set of what? Linearly independent functions. How do we show something's linearly independent? Do the Wronskian. Let's check it out. If we do the Wronskian of the 2 solutions e to the m1x and e to the m2x, we get the determinant of e to the m1x, e to the m2x for the first row. Take the derivatives for the bottom row. That's m1 e to the mx. Sorry, m1 e to the m1x, m2 e to the m2x. Do the determinant, we get m2 e to the m1x plus m2x minus m1 e, and then we just add the exponents. So again, m1x plus m2x we can factor out e to the m1x plus m2x, and we're left with m2 minus m1. And the whole point of doing this was to show that this doesn't equal 0, right? Well, we're halfway there. This never equals 0 because it's an exponential function. Well, what about this part here? Does it equal 0 or not? And why? If m2 equals m1, it equals 0. What was our assumption here, though? Two real distinct roots, right? So, since m1 does not equal m2, this does not equal 0. Therefore, y1, y2, linearly independent. Which means that y1 and y2 form a fundamental set, and the general solution for the differential equation would be y equal to what? If we know y1 works, y2 works, how do we combine them? Good? Good. And that's by the superposition principle. Very good. All right. 1 out of 3 knocked down. Second case. Let's do the easier of the last two. Let's work with this assumption that m1 equals m2. This would be the case where the quadratic is a perfect square, right? The discriminant is 0. We don't get 2 roots, we just get 1. So then y is going to equal, let's call it y1. y1 is going to equal e to the mx and boy, it sure would be nice if someone had shown you how to find a second solution knowing that one of them already works. You guys know what I'm hinting at, right? How do we find the second solution? We're going to use the formula y2, either reduction of order, we're not going to do that, right? Either reduce the order or use the shortcut. y2 is going to equal y1 times the integral of e to the minus integral of p of x dx all over y1 squared okay, but before we can plug everything in, where is our equation? Our original equation was ay double prime plus by prime plus cy equals 0, right? What do I have to do to this before I can plug everything in? Divide by a. So what we want to do is write it as y double prime plus b over a, y prime plus c over a, y equal to 0. So then y2 will be e to the mx integral of e to the minus integral of b over a dx over y1 squared, so we're just going to double the exponent, so 2mx dx and now we actually know a little bit about the solution here. If there's one real root to a quadratic, what is the solution? Think quadratic formula, right? If there's one real root, what happens to the square root? 0, right? So what's left? Negative b over 2a, right? Do you guys see what I'm trying to do here? Maybe not. Here I have this b over a. I don't like that right now. Well, what's b over a going to be? I can multiply by 2. Actually, let's leave it as minus b over a. And that's going to be 2m. Does that make sense? So then I can do this nifty little substitution. Well, yeah, let's go ahead and do that. That's going to be integral of m dx. Oh, forgot my 2, sorry. I'll just put it right there. And if I integrate, this becomes e to the what? 2mx over e to the 2mx. So then this just becomes e to the mx times the integral of dx, which is what? X. Okay. So here's our second solution. Our first solution was e to the mx. What happened for the second one? What's the only difference? Now we just have an x in front of it. Okay? So y1 is equal to e to the mx. y2 is equal to x e to the mx. We'll skip the formalities. These will be linearly independent because the Wronskian will not equal 0. So the general solution, when the characteristic equation has just one root, is going to be equal to c1 e to the root, whatever root we got, times x, plus c2, and then we just do x e to the mx. Okay. Questions on the first two cases? We're doing a lot of work here because I really want to make sure you guys understand and appreciate how quickly we're going to solve these here in just a matter of a few minutes. Okay, so obviously you're not going to derive all this on an exam, but it's nice to know where all these rules and stuff comes from as opposed to here's new diffie q, here is solution, you go solve. Okay, third case. Either two real roots, one real root, or what's the last case? Two complex roots, and they happen to be conjugates, right? So that's where the discriminant is less than 0. So let's let our first root, let's do alpha plus I times beta. And we'll let m2 be its conjugate. And to start, it's similar to case 1. So from case 1, we kind of know what the solution looks like. We know that y is going to equal c1, and then we did e to the m1x, right? So e to the alpha plus, oh, I messed that up, sorry. Alpha plus I beta times x plus c2 e to the alpha minus I beta times x. But these aren't very practical because we have imaginary answers in there. We want to have our functions represented with just real numbers, real coefficients, real functions. Okay, so we're going to kind of break this down and see if we can come up with a better answer. Okay, so we don't want these imaginary exponents. And now here's where we're going to use Euler's identity, Euler's formula, using the fact that e to the I times theta is cosine theta plus I sine theta. We're going to look at the imaginary part of the exponent only. So in the first equation, our imaginary part is e to the ibx, I beta x. And according to Euler's identity, what would this turn into? Cosine beta x. Good. And let's look at the imaginary portion of our second answer. So that's negative I beta x for our exponent. Same thing, just a negative I sine beta x. Okay. And now what we're going to do, first we're going to add these two together. So let's add them. So we get e to the I beta x plus e to the minus I beta x. And you guys kind of know already, right? If you add two conjugates together, what's going to happen? Drop out the imaginary stuff, right? So if I add these two up, and you can see that right here, our I sine beta x goes away. We just get, bless you, we get 2 cosine beta x. Now let's subtract them. We're going to get e to the I beta x minus e to the negative I beta x. And that's simply going to cancel out our real stuff, right? If I subtract two conjugates, the real stuff goes away. And now we get 2I sine beta x. Okay, we'll come back to these later. We'll use these in a little bit. Okay. Real quick, go back here. Call this green equation, let's call it star. Because I'm going to make a reference to it right now. Okay, so from that green equation, from star, to make things easy, let's just make, if we let C1 equal C2 and just make these constants 1 for our first solution, and for our, to get a second solution, we'll do the same idea. We'll do C1 equals 1, though, and C2 equals negative 1. So then let's just write out what that looks like. Then we just have e And all I'm doing is essentially copying down this equation, but I'm using 1 and 1 for our constants for the first solution, and then 1 and negative 1 for y2. So we have e to the alpha plus I beta times x plus e to the alpha minus I beta times x. And then y2, same idea, just subtract, because now c1 is 1, c2 is negative 1. Okay, now you're going to start to see what we did before pay off. Let's look at y1 a little more. What could I factor out from I1? Or y1, sorry. What's one thing that's identical in each term? E to the alpha x. Very good. If I factor out e to the alpha x, what's left? Not just I beta x, but e to the I beta x, right? Plus, what's left from this term? E to the negative I beta x. But hold on a minute. We did this earlier, right? When we added up e to the I beta x and e to the negative I beta x, what did we get? We got 2 cosine beta x, right? So here's our first solution. We get 2 e to the alpha x cosine beta x. So there's y1. Let's look at y2. Same idea. What's the one term in common? E to the alpha x. Pull it out. We get e to the I beta x minus e to the negative I beta x. And we did that earlier. What does that equal? 2, well, don't forget the I for now. 2I sine beta x. So we have 2 times I times e to the alpha x times sine beta x. What's I? Which is a, begins with a C. Constants. So all we really care about is, well, not even the 2. All we really care about is this part. So y2 is going to be e to the alpha x sine beta x. So here's our y2. y1 is right up here. Oh, I'm going over time. Sorry, guys. Let's just finish here then. Same thing as before. Independent. It'll work out. Trust me. You can do the Wronskians yourselves later if you want. So the general solution is going to be y equals c1 e to the alpha x cosine beta x plus c2 e to the alpha x sine beta x, which sometimes we write as factoring out e to the alpha x, and then we just write c1 cosine plus c2 sine. Okay, we have derived everything. We have, like, honestly, 10 more minutes worth of stuff. Maybe we'll try to do both sections tomorrow. Okay, if you want to start the homework, you could probably figure it out, or at least most of it. Drive safe. I don't think your teachers are going to be upset if you're a little late today. Thanks, Juma.